base of the second one. So it becomes your positive gain. So it's a positive gain, so when Vi increasing, V naught is also increasing. Okay, when Vi is increasing, V naught is also increasing. But when? Till it reaches some voltage here. Till Vi reaches some voltage, okay, it is not increasing. At this point, it starts increasing, it goes like that. And after some time, V naught becomes constant. This is a high. This is a low, this is a high. When Q2 was active, this was the voltage at V naught, that is Vc2. V naught is nothing but Vc2. So that is the amplification I am going to get, but here it becomes constant. Below that also it is constant. I think this voltage you can compute, I have written there. How does it come? Now, this is dependent upon the loop gain. Gain of the amplifier, overall gain of the amplifier. Loop gain. So when RC1 is small, first stage amplification becomes small. So you can say loop gain is smaller than 1. First gain itself is very small, so second gain, even if I do that like that, it will be smaller. So it goes like that. So it will be a gain, but gain will come like that because gain is less than 1. So that's what is the characteristic V naught. So loop gain I'm talking, I think you know for control system, meaning of the loop gain that way, including our emitter feedback also it is there, but RC1 controls that loop gain. You know about that. RE and RC are controlling the feedback loop gain or so. So if it is less than 1, it is like this. When I make it 1, by increasing my RC1, I have made the loop gain as 1. Then it will become something like that. It will not go like that, it will take a jump here. So this becomes, if it is equal to 1. Here it was, loop gain was smaller than 1. Here it becomes equal to 1. And when loop gain, feedback gain becomes greater than 1, then the characteristic will be something like that. It is like that. So this is the place here RC1 is large, is sufficiently large. And it is true for all other cases of multivibrators also. Okay, because biasing will be doing. So what happens? If I draw a line here, here loop gain is greater than 1. It goes like that. So here there are 3 voltages coming for Vi. Same Vi. This is my V naught. There are 3 readings coming. I cannot read something in between because it changes very fast from here to here. It is not tracing back like that. It changes from here to this place very fast, decreasing and then becomes constant. So that I will be talking in the module 4 when I will be describing the negative resistance devices. It is going like that. So what do I do? I bias my device. The DC I give this much here. This is the place where I bias now. That means my Vi base of Q1, I can say B1, base of Q1, that is B1, is biased at this point. This much Vi is already there on the base of that. So when I apply my Vt, it becomes that VB1 is, I can say 0, I can put it, initial, So VB10 plus VT will come somewhere here. As a result, I have got this output. Okay. Now, after that, even if voltage is changing, it will be changing in the same up to this point. Okay. Trigger is gone. If when trigger is gone, it is here, going over here, because this trigger is gone, it is at this point. So still it is there. It has not come here. Okay. But my VI DC potential at the base bias is this. I apply a negative trigger from here. Negative trigger brings VI somewhere here. So it will come here. So it will be switching between this low state to high state at the output. And it is working like a bistable multivibrator. Is that okay? So this is all controlled by my RC1 because I'm giving my trigger to the base of the first transistor. Should I give a pause here? I can go ahead now. Okay, fine. This write-up I have uploaded for your convenience. This I have described what is happening with RC1. Coming to the monostable multivibrator. For the monostable multivibrator, it is like that. Let's see. Here is my base. Base is kept open. Here is my resistance. Emitter is coming here. Here is another base. Here also emitters are directly connected. Okay. Then we give a capacitor here. And at this base, remember we have tried to give a positive bias. Here if we go, it will not be that positive bias. So I make positive bias here like a monostable multivibrator. Collector coupled the way I have designed for your case. That is the one. Here is my VCC. So VBB is not coming in this case. VBB was grounded in the previous case. So single power supply I am working. It is this. So this is the way I call this my R and call this my C. This is my RC1 and this is my RC2. Why I am putting? Because T1 and T2 you might be controlling in a different manner. Okay. So this is my RC2 and RC1. I think here only one width is coming. So you can put the same RC1 equal to RC2. That is not changing. This R and C will control the width of the pulse. It will return back to the same stable state. Stable state is, this is my active. This is my active. So that means V0 is low. This is my off. When I applied a positive trigger here, this becomes off. Because same, when I apply here, high current flows, it becomes active, so some current flows. So I1 into RC1, that drop comes here. Same drop is brought here at the base of this. So this becomes off now. That analysis I have given, this becomes off. When this becomes off, at that time no current flows through this. So output becomes your VCC at that time. When trigger is applied, output becomes VCC. Then capacitor starts charging from VCC voltage through R and this C and the equivalent, Thevenin's equivalent here. Thevenin's equivalent is nothing but this RC1. So that way it has come here. So R plus RC1 into this C becomes the time constant tau and capacitor charged like that. It keeps on charging till this becomes something near V gamma, and when it becomes above V gamma, this becomes active. So this becomes V gamma, or you can say greater than V gamma, this becomes active. So at that till that time, I have to find that is the width tau with T. So time constant is R plus R Thevenin's equivalent here, that is RC1 into C. So e to the power minus t divided by this tau, and now t is becoming your something t that makes the voltage here, that V gamma becomes equal to, that way this voltage was Vc1. So Vc1, through that it is getting charged. I think you know the analysis. So this is the way I have written in the diagram. You can see that at t equal to 0 minus Q2 is active, Q1 is off. So these are the voltages at various places. VE becomes your 1 plus 1 by HFE, like that at that time, because your Q2 is conducting. So base current of Q2 is there. At t equal to 0 plus, HFE will not come because base of Q1 is not conducting. Okay, trigger is applied, after that trigger is gone. So at t equal to 0 plus, positive trigger I have applied. These are the voltages at various places. C2 is the second transistor collector, V2 is the second transistors, and 1 etc. are for the first transistor, like that. So that way these voltages are coming. Emitter is the same for both of them. Okay. Now when the capacitor is charging, it becomes your capital T. At that time it is charging through a resistance R plus RC1, and when it reaches a voltage which is VE plus V gamma, that is VB2. VB2 is what? The emitter voltage is also there. With respect to ground, it is VB2. So with respect to ground, VE is your this one plus this V gamma, it becomes greater than that, it becomes active. So till that time it is coming, and this particular T, you know how to compute that, 0.69 RC. Okay, this one will be nothing but QT is active and this one. So here it will be, I was here. So T is 0.69 R plus RC1 into C. So this is the width of the pulse. So RC2 is not coming in the calculation anywhere except for the biasing, but RC2 is independent of the value of RC1. I think that because of that is the beauty of this, your emitter coupled multivibrators. So there is a monostable action. Again a trigger is applied, same process is repeated. So when a trigger is applied, after a width T, the output will come to the zero state, low state, when the Q2 becomes your active. Coming to the, I think diagram I have drawn there, yeah. Coming to the A-stable multivibrator case, A-stable multivibrator, emitter coupled A-stable multivibrator. This one is something like this. Water coupling there. Here also base is kept open. This is your resistance RC1. I think I need not write this value, you already know. Here the resistances are different. This becomes my RE1, and here is RE2. Why? You may make the same thing, but there are two separate resistances, remember. RE1 can, RE2 may be having the same value or different value. Okay, this is RC1, this I am putting as my RC2. Okay, this is my VCC supply. What is the coupling? This is coming and getting connected to the base directly. So this becomes our A-stable multivibrator. So circuit assembly is very simple. And here what happens? This is your active. This one is your off. Here I have already given not a trigger, a DC voltage, VBB, positive voltage I am giving here. Always a positive voltage is connected. When t equal to 0 minus, I am saying that time I start observing the circuit. So t equal to 0 minus, I am observing the circuit. So what is going to happen? At t equal to 0 minus, observing this is active, this is my off. So at the various places, VC2, VC1, etc., what are the voltages that I have made here? I am interested in VC2. VC2 is VCC minus I2RC, that is low. That is low. Initially at t equal to 0 minus, observation is that it is low. Then what happens? At that time, this capacitor is charging. It is low, so current is flowing through this. And this IB is also coming. So this IC1 plus this IC2, I2 is your IC2, IB2 is coming from here. Okay, that is your VCC. The off, so VCC comes here. Okay, if it is off, that means VCC is coming here. So this VCC and this VE, the difference here is your VB. Okay, so that way your IB is there, this voltage minus this voltage will be coming like that, and that into RE1 will be giving you this voltage. Capacitor will be charging through that. So what is being done here is two current, this one current and this current, both are passing through this capacitor and through this RE1 like that. So your RC2 will control the T1, that is the duration when it is low. RC2 is low, it is active till capacitor is charging. When the capacitor charges to some voltage such that this voltage minus this base minus emitter voltage becomes smaller than V gamma or equal to V gamma, at that time it becomes off. When that becomes your off, at that time this one will become high. So that T1, if I mark that this one as my T1, if I'm marking this one as my T1, I'm marking this one as my T1 and this one is my T2. Then T1 is controlled by RC1. Same RC1 and RC1 and RE2. RC1 and RE2 is controlling my T1. T2 will be controlled by RC2 and RE1. So that way it will be having oscillation T1 and T2 if the two are different, and this may be same, may be different. As I given you the idea, that way you can design your circuit like that. So here the respective voltages are coming like that. VC2 is like this, because look, this is directly connected, so no further current is coming. So when this becomes your active, that VCC minus I1 RC, it is not IC1, I1 into RC1 is the drop. So how to find that I1? If it has become active region, how much voltage is coming here? That you have to find out how does it come. When it is active, how much is your VCE in that bias condition, transistors manufacturing condition, that you add. So your RE1. So this VBB is here. VBB plus your something like VBB minus VBE becomes your this thing, and this plus VCE becomes your this thing, VC1. So that way active region you can find. When this voltage is obtained, VCC minus this VC1 divided by RC1 becomes the current I1. So you can find what is my this one, that is my IB2, because this is your off. When this is your active, this becomes your off. So at that time IB2 if is 0, it will be passing entire current through this. So you can calculate like that, you know that things. And capacitor is charging. When it is charging, this voltage is now rising. Okay, because initially this was drop from here to a major drop was there. That IC was coming, it was passing through that, so this voltage was smaller. Now when it has become off, this voltage becomes larger, but there is no current flowing through that. So this part I am taking. So RE1, whatever change is there here, same thing is brought here. Similarly, whatever change is here, same thing is brought here also. So that way it will be switching between active and off stages. So this analysis I have given about VE1 at T equal to this T1. Okay. Similarly for T2 you will have to work at T equal to T1. This you have to find by the relationship that VE2 at T equal to 0 plus minus VE2 at T equal to, let us say, tau 1. That will be the same as this one, VE1 at 0 plus, T equal to 0 plus, minus VE1 at T equal to tau 1. So that difference gives me, okay, that difference gives me this difference equal to this difference, and here I have computed both of them for VE2. So here VE2 at T equal to tau capital T1, I can compute by that. When the cycle reverses, it will be for the capital T2 now. So it will not be a 0 plus, it will be fluctuating from T equal to T1. When you go for the 0 plus, that will be your T2 coming into that place. So T1 has brought this change from this state to some other state, it has brought the change. Now again, when I go for T2, it will be brought to the same state. So 0 plus will not be coming in this analysis. So it will become, afterwards it was T1 and T2 will be the marking point, and a stable multivibrator oscillates. So these are called emitter coupled multivibrators. And I have posted this file. Diagrams are not there, but diagrams are given in the book also. I'll give in the file, maybe by tomorrow or so. I'll make it like that. So this is the way. Professor Sen Gupta, is there?
Yes, sir. Yes, sir.
So let me ask students if any doubt from today's talk. I've gone slightly faster because in the last class yesterday, I gave you some kind of in a very slow kind of delivery. I have given you that what is happening in those various places. Now this write-up is there with you. You have to consider T1 I have given, then going to 0 plus will be your T2. It will not be your, after that 0 plus it will be T2 in that case. So that way it will be your T1 and T2, and that will keep on repeating after every interval of T1 and T2 like that. So a stable multivibrator will be there. Question? No question. Then Professor Sen Gupta will summarize this whole thing that I have taught using transistor. He will summarize the things with the help of operational amplifiers. Am I correct, Professor Sen Gupta?
Yes, sir. I will give some.
Yeah, okay, sir. So he will summarize that, and he may, prefer you to stay for a couple of minutes extra. So Professor Sen Gupta, yes, you can take now. I have
yes, sir.
Stopped my presentation now.
Okay. Thank you, sir. So is my screen visible?
Yes, sir.
Okay. So whatever the multivibrator you have studied, those can be implemented very easily using op-amp. So you know that op-amp is a very useful device. So we can design those multivibrator using op amp. So I will briefly discuss on the basic concepts how the op amp is used for creating the states like stable state, quasi-stable state, and according to their use for multivibrators like astable, monostable, and bistable. So before that, I am showing you one circuit that is Smith trigger. Smith trigger using op amp. So and this principle is used for multivibrator also. So you see that this op amp it has two terminals. One is inverting terminal, another is non-inverting terminal. So here in the non-inverting terminal, we connect one resistance. Basically, two resistance R1 and R2 are there, which is connected in series with output voltage output of op amp V0, and from the or across the voltage across the resistance R2, okay, we take the feedback and apply to the non-inverting terminal. So whatever the voltage is coming across this resistance R2 is always present in the non-inverting terminal. So this way, this feedback is given to the input to the op amp. So now what is the role of this? That this op amp you see that works in comparator uh, mode of operation. So comparator means the two voltages at inverting and non-inverting terminals are compared, and according to the output V0 is generated. Okay, so that means two voltage is if V0, that is voltage at negative terminal, non-inverting terminal, and voltage at non-inverting terminal. So if voltage at inverting terminal is greater, okay, than non-inverting terminal, like say if it is 2 volt and if it is 3 volt, if it is 3 volt and if it is 2 volt, okay, then output of op amp produces negative voltage, that is minus V sat, okay, saturation voltage minus V sat, and which is what? Say if you apply plus 10 volt here and the minus 10 volt, so plus 10 volt would be the plus V sat and minus 10 volt is the minus V sat. Okay, so these are the two saturation voltage. What's now? So if you apply 3 volt at the negative terminal and 2 volt at the positive terminal, so more voltage is there in the inverting terminal, so output will be negative minus V sat. Similarly, if V negative is less than V positive, okay, that means say if it is 2 volt and if it is say 3 volt, then output will be equal to plus V sat. So this is the principle. That means more voltage is coming at the in non-inverting terminal, so output will be plus V sat. So this concept you have to keep in mind, okay, to understand the operation of Smith trigger or any multivibrator circuit. Now we take the some fraction of voltage of output which is coming across R2 is applied at the plus terminal of the op amp. So that voltage is how much? That voltage is that threshold voltage VTH. Okay, so VTH is given by V0 by R1 plus R2 into R2. Now this R2 divided by R1 plus R2 is what? It is the beta, that is feedback factor. Feedback factors, okay, this beta. So now VTH is beta V0. Now this threshold voltage may be positive, may be negative, because V0 takes two values, either positive plus V sat or minus V sat. Okay. Now to understand the operation, first you have to assume that any state at the output. So initially we assume that at t is equal to 0 minus, say, at t is equal to 0 minus, let us say V0 is equal to plus Vsat. Okay. V0 is at plus Vsat. So we get this voltage at this point, that is plus beta Vsat. Okay, that is feedback voltage. Now this voltage is called upper threshold voltage, and when beta V naught and when V naught is negative minus Vsat, that time we get minus beta V naught. So first we assume that Vsat is staying at, the output is staying at plus Vsat. Okay, so this voltage is positive, and initially say input voltage is 0. Okay, I'll show the waveform. Initially input voltage is 0 volt, say, and this voltage, this plus Vsat is there, so it is some positive value. So the output will stay at plus Vsat. Okay? It will remain at plus Vsat. Now the input voltage is rising, okay, from 0 volt. The input voltage is rising from 0 volt sinusoidally, say. So what happens? Initially output is, so this is input voltage Vi, and this is say output voltage V naught. So initially say we say output is staying at plus Vsat. So and input is increasing from 0 volt, 0 volt. So a time will come when input voltage will cross the voltage, that is threshold voltage VUT. Okay, that is equal to plus Vsat, because it is a voltage across R2 which is coming here, and input is changing. So when input voltage will become just slightly greater than this upper threshold voltage VUT, that time what happens? The op-amp state will change. Okay, op-amp state will change from plus Vsat to minus Vsat. Okay, so this time uh, because this time more voltage is coming across the input, across the inverting terminal, okay, than the non-inverting terminal. But at that time what happens? Similarly, the voltage drop across R2 will be negative. Okay, will be negative there. Now it has become negative because output is now minus Vsat. So some drop is there, that is equal to that minus beta Vsat. Okay. That is now coming minus Vsat. And that time you see input voltage is positive, okay, because it is sinusoidal. It is positive now. So the state will be maintained, that minus Vsat at the output will be maintained until and unless the, so we see the draw, you see the voltage drop in the waveform. So let us mark one another point here in the sine wave. Okay, this point. So this is a lower threshold voltage VLT. Okay, so the time will come when the input voltage will just cross this lower threshold voltage VLT, or it will be lower than that voltage. Okay, so that time what happens? Less voltage will be coming at the negative terminal. Okay, so what happens? The output state will change. Okay, from minus Vsat to plus Vsat. Okay. So it will again be maintained there. Okay, so this way you see again here another voltage level is this plus, when again input voltage will cross this threshold voltage, then again there will be switching, change the state. So what happens? The sine wave is converted to a square wave. Okay. So what I have drawn, what I have shown you have drawn in better diagram, in better way. So you see, you can understand here that input voltage is sinusoidally changing, and when input voltage is crosses the positive threshold voltage, that time output switches from plus Vsat to minus Vsat. So this is the operation of Smith trigger, and this is the hysteresis graph that you can understand. Sir has also described earlier what is hysteresis. Okay, now we go to the astable multivibrator using op-amp. So here in the feedback stage, you see it remains same, that is R1 and R2. R1 and R2 are present, and we take the voltage drop across R2 and apply it in the non-inverting terminal. But here we use some RC circuit. Okay. So here in the feedback resistance, feedback path resistance RF and capacitor C. So what happens in this case? In the earlier case, we compared a sine wave with the threshold voltage. Okay, sine wave was the input. Now here we compare the sine wave with the threshold voltage. But in this case, we compare the voltage across output, which is actually it will be actually charging and discharging kind of waveform. Okay, so that voltage will be compared with the this threshold voltage, and accordingly output will be automatically generated. So here no input voltage actually we externally apply. Okay, but we get some square wave at the output. Square wave at the output. Now what is the operation? Now I explain here. So let us see, let us first assume that output is staying at plus Vsat initially. Okay, plus Vsat initially. So, and you see this is actually V naught. I just draw that part only, the RC circuit part. Okay, so that output voltage V naught is staying at plus Vsat voltage initially, say, and that time what happens, capacitor is initially 0 volt discharged, or 0 volt, say. Now it will start charging from that value, and uh, what happens that you see the diagram that here plus Vsat is there, plus Vsat is the voltage. Now here we get plus beta into Vsat, some positive voltage, and that voltage, okay, that voltage is say here again I draw, let me draw here. Okay. So here initially say output is V naught and staying at plus Vsat. Okay. So, and capacitor, say I am drawing, say it is actually, say let us say it is charging from 0 volt, and time will come when the capacitor voltage will reach this plus Vsat value, and will be more than that. When it will be more than that, okay, that time what happens? Say this voltage is, capacitor voltage has reached to plus beta Vsat. Okay. When capacitor voltage is reached that value, and slightly more than that, that time what happens? More voltage will appear at the negative terminal. So what happens? The op-amp will immediately switch to negative voltage, minus Vsat. Okay, again negative voltage to minus Vsat. Sorry, it will switch to minus Vsat. So minus B set. Now what happens when minus B set? So that time the voltage across resistance become minus beta V set. So but at the same time also this output voltage become actually is minus V set. So now you see the capacitor actually which was charged to plus Vsat plus beta Vsat. Now it will try to charge to minus Vsat or try to discharge. That is because negative voltage. So from that point it will start discharging. Okay, it will start discharging. And when this capacitor voltage will reach to this value minus beta Vsat, let us say this value, because this voltage is appearing here at the positive terminal. So when the voltage will be, capacitor voltage will be lesser than that minus Vsat, lesser than minus Vsat. That means less voltage is at the negative terminal and more voltage is at the positive terminal. Okay. So what will happen? Again, more voltage is at plus terminal of the op amp. So op amp state will change to from minus Vsat to plus Vsat. So again the capacitor will start charging from this value minus beta Vsat to again plus Vsat. Again it will there will change in the state when it will reach to plus beta Vsat. So this is the operation. Is there any doubt?
No, sir.
Okay, you can tell anything if you have any doubt.
Okay, thank you, President Gupta. Okay,
Yes, sir.
friends, so now we know from all the aspects, we have seen the multivibrators using op amp and using the transistors. So I think you will be able to design any kind of oscillator that comes to your need. Okay, so given the your direct coupled also.
Sir, one another equation, some one or two topics are there. Just let me show that one. So
Quickly, there's something because they have
yes,
to leave
yes,
quickly.
yes, yes, yes. So what is the equation I have given in the diagram? Okay, so what is the time period? Okay, I have mentioned they have drawn the calculated the time period. So that is based on the in that formula that we have seen in the case of RC circuit. Okay, that is based on initial value and final value. Okay, initial value and final value equation VI VF. Okay, is that formula we have used and we have calculated the time period. And then similarly monostable multivibrator is used. Okay, so here across the capacitor we have used one diode, and here use one RC circuit to provide trigger. So everything is explained in the file, okay, in the PPT. So you just go through it, and if you have any doubt, you can ask. Okay. So here also I have given the notes on bistable multivibrator. We just go through it, and